Today we are going to learn about linear regression in Python. I will try to explain everything from simple linear to multiple, polynomial and advanced linear regression. I will also walk you through the source code, and if you want to download the source code, you find the link to it in description. Linear regression is one of the fundamental statistical and machine learning techniques. Whether you want to do statistics, machine learning, or scientific computing, there's a good chance that you'll need it. It's best to build a solid foundation first and then proceed toward more complex methods. By the end of this video, you'll have learned what linear regression is, what it is used for, how it works, and how to implement linear regression in Python. Let's first understand what regression is. Regression searches for relationships among variables. For example, you can observe several employees of some company and try to understand how their salaries depend on their features, such as experience, education level, role, city of employment, and so on. This is a regression problem where data related to each employee represents one observation. The presumption is that the experience, education, role, and city are the independent features, while the salary depends on them. Similarly, you can try to establish the mathematical dependence of housing prices on area, number of bedrooms, distance to the city center, and so on. Generally, in regression analysis, you consider some phenomenon of interest and have a number of observations. Each observation has two or more features. Following the assumption that at least one of the features depends on the others, you try to establish a relation among them. In other words, you need to find a function that maps some features or variables to others sufficiently well. The dependent features are called the dependent variables, outputs, or responses. The independent features are called the independent variables, inputs, regressors, or predictors. Linear regression. Linear regression is probably one of the most important and widely used regression techniques. It's among the simplest regression methods. One of its main advantages is the ease of interpreting results. When implementing linear regression of some dependent variable y on the set of independent variables x equals x, where is the number of predictors, you assume a linear relationship between y and x, y equals beta x plus beta x plus epsilon. This equation is the regression equation. Beta are the regression coefficients, and epsilon is the random error. Linear regression calculates the estimators of the regression coefficients, or simply the predicted weights, denoted with. These estimators define the estimated regression function, equals plus x plus midline horizontal ellipsis plus x. This function should capture the dependencies between the inputs and outputs sufficiently well. The estimated or predicted response, for each observation equals 1, should be as close as possible to the corresponding actual response y. The differences y, for all observations equals 1, are called the residuals. Regression is about determining the best predicted weights, that is, the weights corresponding to the smallest residuals. Simple linear regression. Simple or single-variate linear regression is the simplest case of linear regression, as it has a single independent variable, equals x. The following figure illustrates simple linear regression. When implementing simple linear regression, you typically start with a given set of input-output, xy pairs. These pairs are your observations, shown as green circles in the figure. For example, the leftmost observation has the input x equals 5 and the actual output, or response, y equals 5. The next one has x equals 15 and y equals 20, and so on. The estimated regression function, represented by the black line, has the equation, x equals plus x. Your goal is to calculate the optimal values of the predicted weights and that minimize SSR and determine the estimated regression function. The value of, also called the intercept, shows the point where the estimated regression line crosses the y-axis. It's the value of the estimated response, x, for x equals 0. The value of determines the slope of the estimated regression line. The predicted responses, shown as red squares, are the points on the regression line that correspond to the input values. For example, for the input x equals 5, the predicted response is 5 equals 8.33, which the leftmost red square represents. The vertical dashed gray lines represent the residuals, which can be calculated as y equals y, x for equals 1. They're the distances between the green circles and red squares. When you implement linear regression, you're actually trying to minimize these distances and make the red squares as close to the predefined green circles as possible. Multiple linear regression. Multiple or multivariate linear regression is a case of linear regression with two or more independent variables. If there are just two independent variables, then the estimated regression function is x2 equals plus x plus 2x2. It represents a regression plane in a three-dimensional space. The goal of regression is to determine the values of the weights, and two such that this plane is as close as possible to the actual responses, while yielding the minimal SSR. Polynomial regression. You can regard polynomial regression as a generalized case of linear regression. You assume the polynomial dependence between the output and inputs and, consequently, the polynomial estimated regression function. In other words, in addition to linear terms like x, your regression function can include nonlinear terms such as 2x superscript 2, 3x superscript 3, or even 4xx2, 5x superscript 2x2. The simplest example of polynomial regression has a single independent variable, and the estimated regression function is a polynomial of degree 2, x equals plus x plus 2x superscript 2. Now, remember that you want to calculate, and 2 to minimize SSR. These are your unknowns. Keeping this in mind, compare the previous regression function with the function x2 equals plus x plus 2x2 used for linear regression. They look very similar and are both linear functions of the unknowns, and 2. This is why you can solve the polynomial regression problem as a linear problem with the term x superscript 2 regarded as an input variable. In the case of two variables and the polynomial of degree 2, the regression function has this form x2 equals plus x plus 2x2 plus 3x superscript 2 plus 4xx2 plus 5x2 superscript 2. The procedure for solving the problem is identical to the previous case. You apply linear regression for 5 inputs x2, x superscript 2, xx2, and x2 superscript 2. As the result of regression, you get the values of 6 weights that minimize SSR, 2, 3, 4, and 5. Underfitting and overfitting. One very important question that might arise when you're implementing polynomial regression is related to the choice of the optimal degree of the polynomial regression function. There's no straightforward rule for doing this. It depends on the case. You should, however, be aware of two problems that might follow the choice of the degree: underfitting and overfitting. Underfitting occurs when a model can't accurately capture the dependencies among data, usually as a consequence of its own simplicity. It often yields a low superscript 2 with known data and bad generalization capabilities when applied with new data. Overfitting happens when a model learns both data dependencies and random fluctuations. In other words, a model learns the existing data too well. Complex models, which have many features or terms, are often prone to overfitting. When applied to known data, such models usually yield high superscript 2. However, they often don't generalize well and have significantly lower superscript 2 when used with new data. The next figure illustrates the underfitted, well-fitted, and overfitted models. The top left plot shows a linear regression line that has a low superscript 2. It might also be important that a straight line can't take into account the fact that the actual response increases as x moves away from 25 and towards 0. This is likely an example of underfitting. The top right plot illustrates polynomial regression with the degree equal to 2. In this instance, this might be the optimal degree for modeling this data. The model has a value of superscript 2 that's satisfactory in many cases and shows trends nicely. The bottom left plot presents polynomial regression with the degree equal to 3. The value of superscript 2 is higher than in the preceding cases. This model behaves better with known data than the previous ones. However, it shows some signs of overfitting, especially for the input values close to 60, where the line starts decreasing, although the actual data doesn't show that. Finally, on the bottom right plot, you can see the perfect fit, 6 points, and the polynomial line of the degree 5, or higher, yields superscript 2 equals 1. Each actual response equals its corresponding prediction. In some situations, this might be exactly what you're looking for. In many cases, however, this is an overfitted model. It's likely to have poor behavior with unseen data, especially with the inputs larger than 50. Python packages for linear regression. It's time to start implementing linear regression in Python. To do this, you'll apply the proper packages and their functions and classes. NumPy is a fundamental Python scientific package that allows many high-performance operations on single-dimensional and multidimensional arrays. It also offers many mathematical routines. Of course, it's open source. The package sklearn is a widely used Python library for machine learning, built on top of NumPy and some other packages. It provides the means for pre-processing data, reducing dimensionality, implementing regression, classifying, clustering, and more. Like NumPy, sklearn is also open source. If you want to implement linear regression and need functionality beyond the scope of sklearn, you should consider stats models. It's a powerful Python package for the estimation of statistical models, performing tests, and more. It's open source as well. Simple linear regression with sklearn. You'll start with the simplest case, which is simple linear regression. There are 5 basic steps when you're implementing linear regression. Import the packages and classes that you need. Provide data to work with, and eventually do appropriate transformations. Create a regression model and fit it with existing data. Check the results of model fitting to know whether the model is satisfactory. Apply the model for predictions. These steps are more or less general for most of the regression approaches and implementations. Throughout the rest of the tutorial, you'll learn how to do these steps for several different scenarios. Step 1. Import packages and classes. The first step is to import the package NumPy and the class linear regression from sklearn.linear_model. Now, you have all the functionalities that you need to implement linear regression. The fundamental data type of NumPy is the array type called numpy.array. The rest of this tutorial uses the term array to refer to instances of the type numpy.array. You'll use the class sklearn.linear_model.linear regression to perform linear and polynomial regression and make predictions accordingly. Step 2. Provide data. The second step is defining data to work with. The inputs, regressors, x, and output, response, y, should be arrays or similar objects. This is the simplest way of providing data for regression. Now, you have 2 arrays, the input, x, and the output, y. You should call .reshape on x because this array must be 2-dimensional, or more precisely, it must have 1 column and as many rows as necessary. That's exactly what the argument, -1, 1, of .reshape, specifies. This is how x and y look now. As you can see, x has 2 dimensions, and x.shape is 6, 1, while y has a single dimension, and y.shape is 6. Step 3. Create a model and fit it. The next step is to create a linear regression model and fit it using the existing data. Create an instance of the class linear regression, which will represent the regression model. This statement creates the variable model as an instance of linear regression. You can provide several optional parameters to linear regression. Fit_intercept is a boolean that, if true, decides to calculate the intercept or, if false, considers it equal to 0. It defaults to true. Normalize is a boolean that, if true, decides to normalize the input variables. It defaults to false, in which case it doesn't normalize the input variables. Copy_x is a boolean that decides whether to copy, true, or overwrite the input variables, false. It's true by default. N_jobs is either an integer or none. It represents the number of jobs used in parallel computation. It defaults to none, which usually means 1 job. -1 means to use all available processors. Your model as defined above uses the default values of all parameters. It's time to start using the model. First, you need to call .fit on model. Your model as defined above uses the values of the weights of all parameters. Using the existing input and output, it's time to start using the model as the arguments. First, you need to call .fit on model fits the model. It returns self, which is the variable model itself. That's why you can replace the last two statements with this one. This statement does the same thing as the previous two. It's just shorter. Step 4. Get results. Once you have your model fitted, you can get the results to check whether the model works satisfactorily and to interpret it. You can obtain the coefficient of determination, superscript 2, with .score, called onModel. When you're applying .score, the arguments are also the predictor x and response y, and the return value is superscript 2. The attributes of model are .intercept underscore, which represents the coefficient, and .coef_, which represents. The code above illustrates how to get n. You can notice that .intercept_ is a scalar, while .coef_ is an array. The value of is approximately 5.63. This illustrates that your model predicts the response 5.63 when x is 0. The value equals 0.54 means that the predicted response rises by 0.54 when x is increased by 1. You'll notice that you can provide y as a two-dimensional array as well. In this case, you'll get a similar result. This is how it might look. As you can see, this example is very similar to the previous one, but in this case, .intercept_ is a one-dimensional array with the single element, and .coef_ is a two-dimensional array with the single element. Step 5. Predict response. Once you have a satisfactory model, then you can use it for predictions with either existing or new data. To obtain the predicted response, use .predict. When applying .predict, you pass the regressor as the argument and get the corresponding predicted response. This is a nearly identical way to predict the response. In this case, you multiply each element of x with model.coef_ and add model.intercept_ to the product. The output here differs from the previous example only in dimensions. The predicted response is now a two-dimensional array, while in the previous case, it had one dimension. If you reduce the number of dimensions of x to 1, then these two approaches will yield the same result. You can do this by replacing x with x.reshape, -1, x.flatten, or x.revel, when multiplying it with model.coef_. In practice, regression models are often applied for forecasts. This means that you can use fitted models to calculate the outputs based on new inputs. Here .predict is applied to the new regressor x_new and yields the response y_new. This example conveniently uses a range from numpy to generate an array with the elements from 0, inclusive, up to but excluding 5, that is, 0, 1, 2, 3, and 4. Multiple linear regression with sklearn. You can implement multiple linear regression following the same steps as you would for simple regression. The main difference is that your X array will now have 2 or more columns. Steps 1 and 2, import packages and classes, and provide data. First, you import numpy and sklearn.linear_model.linear regression and provide known inputs and output. That's a simple way to define the input X and output Y. You can print X and Y to see how they look now. In multiple linear regression, X is a two-dimensional array with at least 2 columns, while Y is usually a one-dimensional array. This is a simple example of multiple linear regression, and X has exactly 2 columns. Step 3. Create a model and fit it. The next step is to create the regression model as an instance of linear regression and fit it with .fit. The result of this statement is the variable model referring to the object of type linear regression. It represents the regression model fitted with existing data. Step 4. Get results. You can obtain the properties of the model the same way as in the case of simple linear regression. You obtain the value of superscript 2 using .score, and the values of the estimators of regression coefficients with .intercept_ and .coef_. Again, .intercept_ holds the bias, while now .coef_ is an array containing and 2. In this example, the intercept is approximately 5.52, and this is the value of the predicted response when x equals x2 equals 0. An increase of x by 1 yields a rise of the predicted response by 0.45. Similarly, when x2 grows by 1, the response rises by 0.26. Step 5. predict response. Predictions also work the same way as in the case of simple linear regression. The predicted response is obtained with .predict, which is equivalent to the following. You can predict the output values by multiplying each column of the input with the appropriate weight, summing the results, and adding the intercept to the sum. You can apply this model to new data as well. That's the prediction using a linear regression model. Polynomial regression with sklearn. Implementing polynomial regression with sklearn is very similar to linear regression. There's only one extra step. You need to transform the array of inputs to include nonlinear terms such as x superscript 2. Step 1. Import packages and classes. In addition to numpy and sklearn.linear_model.linear regression, you should also import the class polynomial features from sklearn.preprocessing. The import is now done, and you have everything you need to work with. Step 2a. Provide data. This step defines the input and output and is the same as in the case of linear regression. Now you have the input and output in a suitable format. Keep in mind that you need the input to be a two-dimensional array. That's why .reshape is used. Step 2b. Transform input data. This is the new step that you need to implement for polynomial regression. As you learned earlier, you need to include x superscript 2, and perhaps other terms, as additional features when implementing polynomial regression. For that reason, you should transform the input array x to contain any additional columns with the values of x superscript 2, and eventually more features. It's possible to transform the input array in several ways, like using insert from numpy. But the class polynomial features is very convenient for this purpose. Go ahead and create an instance of this class. The variable transformer refers to an instance of polynomial features that you can use to transform the input x. You can provide several optional parameters to polynomial features. Degree is an integer, 2 by default, that represents the degree of the polynomial regression function. Interaction_only is a boolean, false by default, that decides whether to include only interaction features, true, or all features, false. Include_bias is a boolean, true by default, that decides whether to include the bias, or intercept, column of 1 values, true, or not, false. This example uses the default values of all parameters except include_bias. You'll sometimes want to experiment with the degree of the function, and it can be beneficial for readability to provide this argument anyway. Before applying transformer, you need to fit it with .fit. Once transformer is fitted, then it's ready to create a new, modified input array. You apply .transform to do that. That's the transformation of the input array with .transform. It takes the input array as the argument and returns the modified array. You can also use .fit_transform to replace the 3 previous statements with only one. With .fit_transform, you're fitting and transforming the input array in one statement. This method also takes the input array and effectively does the same thing as .fit and .transform, called in that order. It also returns the modified array. This is how the new input array looks.